Hello 406 people, Dr. Keith Schubert. Today we're going to be talking about interest and engineering economics and things of this sort. So when we start talking about engineering economics, we're talking about how things cost. And since for us in engineering, future costs are going to affect how our designs are received and whether it's a good buy, and the rest of this we have to talk a little bit about money and interest rates and wonderful fun things like this. This also is kind of a good thing when you're planning your futures as well. So let's consider a simple thing. We're going to consider P to be our present worth, and what we want to do is try to find out what is the future worth of something, which we'll do with F, if I take this simple piece of principal and I'm going to charge interest on it. Now let's say I charge an interest rate of I, and I'm going to have that interest rate of I apply, let's say, just one time. So there's one period on which I am dealing with this. So I pay interest on the principal P. So what my future worth is what I am presently have plus whatever the interest rate is times P. This is kind of the gain that it's going to encounter. And we often write this by pulling the P out, and then we have 1 plus I. So that's what happens if there's one period that goes on to this. Now, if you were doing simple interest, you would just repeat that over and over again. But it actually does happen in some areas, Africa and places like that often will use simple interest, although compound interest is what you will find in the United States and most of the major developed countries. Now, what happens with compound interest is we say at the end of one time period, this is what you have. And this is kind of your new principal at the end of that time period. So next time you pay, you have this as your base. So now if this is 1 year into the future, future worth 2 years into the future, I have my 1 year into the future, plus I have to pay interest on my principal, which is now 1 plus I. I have a new principal value that's in there. So when I do this, again now P1 plus I is common, and I've got 1 here and an I here, so I pull it out and I get P1 plus I times 1 plus I. This 1 comes from this term, this I comes from I times the same term, which is just equal to P1 plus I quantity squared. Now, if you notice pretty easily, we can go, wow, 1 year into the future it's 1, 2 years into the future it's 2, therefore we can conjecture into the future that, some future, let's say n years into the future, this must be P1 plus I. The n. You can obviously repeat this process calculating ad infinitum, and you are indeed correct. That is what you end up getting. Now, usually when we're taking a look at this formula, we are considering this as measuring in years as our period. This is kind of the standard bank assumption. Your interest rate is based off of years. So this is when they give you an APR, that's what they're giving you. So this is kind of your APR number. Now you might be aware that there's another number that comes in, which is your API, and then they sometimes compound more than a year, even though they talk about an APR as it goes. So what is the deal with that one? Well, if I want to go and switch to a more frequent compounding, now, I could just keep using the same rate, but nobody's going to want to pay some ridiculously high interest rate every single month. What they do is they say, hey, look, this is your APR. Right? So I is equal to our APR, annual percentage rate. They say what we're going to do, let's say we're going to compound this monthly. So they will say that your I is equal to whatever rate we're going to charge you every single month or period or whatever, times the number of periods, M, that I'm going to break it into. M would be 12, for instance, if it was months. If I go to daily, it's 365, so on and so forth. So that we find out the rate at which they are going to compound it every day is just your APR, interest rate I, divided by the total number of periods that they're going to do it in a year. So that's what they get as their thing. And this I over m is now the rate that they use. So when they calculate their future values using this rate per month, but now there's m of them per year, and there are n years, so your future is then p1 plus I over m to the nm. And that's if you are using your APR. You can also rewrite this by just noting that I over m is r. I over m is r, so you can just write it in that fashion. Now, there's another term that I've mentioned, which is APY. And the APY I'm going to call RE, right? An effective rate that's going on. And this is your annual effective rate. And what happens here is people note, hey, look, if I just consider this, let's just do 1 year. Right? And just say $1 1 year. So let me just consider $1 1 year. Actually, let me write it off to the side here. So if I'm doing $1 for 1 year, I have this 1 plus r to the m. You know, or I can say instead of r, we can do this as I over m. All right. So now I've got this term. And I note that this is a little bit bigger than 1 as it goes. So therefore, the amount that this is bigger than 1 must be an interest rate of some type. Right, this is my APY, is that it's bigger than 1, so I take this, I subtract 1 out, and that then gives me my rate effective, or your APY. So if you just take this part of the formula here, raised to m, your yearly amount, it's not going to end up to be 1, right, because this was kind of a forced formula that they went on, and so the difference between that is effectively what they are charging you. They are, in reality, charging you more than they claim when they give you an APR. Now, for small numbers, it's fairly close. As those numbers get big, it deviates pretty strongly. As you compound it over years, it deviates pretty strongly too. Now, if you make this definition, then you can also get one more thing for f, which is f is equal to p 1 plus rate effective, and now you can just do to the n, and it's a little bit cleaner because you've calculated that one term as it goes. Now, this is a formula we use all the time. Right? So, you know, it's a very common one, and so this is something we often deal with, and so we actually tabulate this. But we tabulate it by taking, we don't want this p, we can't tabulate all those, so we divide both sides. So we just find that f over p is equal to 1 plus some rate to some period. And now I'm not calling r this, I'm not mentioning which one it is. It's some rate to some period. You determine this by the rate and the periods you do it. So if you're using I over m, then your k will be nm. If you're using RE for R, then N is going to be your, or K will be N. You know, so you can handle that as you want to go. It's going to be one of those two terms, depends on the period you want to go on. It'll give you the same answer because that's how we calculate RE. So this gives us a nice way to simply do this, and we can tabulate this. It's principal independent, so you can actually find tables of this. You know, f over p, it's your, you know, single payment compound amount factor, and it makes it a nice easy way of handling it. Now, if you don't have a table readily available to you, you know, it can be kind of challenging to figure out some basic ideas of estimating what's going on. So there's a fun way of figuring out what this is going to look like. Now, we can't obviously do this for, you know, it's an exponential, so you can't perfectly do this for everything, but we can estimate it for a simple thing. How long is it going to take to double? Right? So that's the question that comes on. So we say, you know, when does it double? Well, it's going to double when 1 plus r to whatever your k factor is whenever this is met for some r and k. Now, how do we figure out how to solve this? Well, what we're going to do to get our estimate is I'm going to take the natural log of both sides. Natural log of 2 has to be equal to, and using the properties of logs, the exponent's going to come out, so we get this. Okay? Now, when we go through on here, we go, okay, wonderful. And this now is equal to, and we can solve for k. How long is that going to be? That's got to be equal to the natural log of 2 divided by the natural log of 1 plus r. Now, natural log of 2 is approximately equal to 0.69, the first two decimal places of it. Natural log of 1 plus r, assuming r is, if it's like 6% interest or something, natural log of 1.06 is pretty close to 0.06. So when you get really close to 1, it's fairly straight. So this is a nice little approximation on here that this ends up giving me something pretty darn close to r. Now, what that means is this r is something like 0.06, and this is 0.69. I can also just treat this as equal to 69 over r as a percent. So if somebody says I have 6% interest, then r is equal to 6, because I've just shifted the decimal place for both, so you don't have to do the 0.06. It's just conceptually a little bit easier for people. You can use 69, you can use 70, 69 is a little bit closer, things of that sort. But just as a little sample on this, let's say r was 3. So if you took 69 divided by 3, you would have 23. So I'd say, I want to see how long at 3% interest is it going to take for my money to double. And this says approximately 23 years to double your money at 3% interest. A long time. Now the question is, how close is that? Well, if you took 1.03 and raised it to the 23, you would get 1.97 and stuff. Pretty darn close to 2. It's a good approximation. Right? So it's a lousy interest rate, but it's a good way to approximate, how long is it going to take to approximately double. And then if you want something bigger, if you say, hey, look, what's going to happen in 40 years? Well, it's going to be a little bit less than 4 times. So you got a nice way to kind of ballpark this, because in 46 years, it will have doubled twice, which means it's going to be around 4. So if you're at 40 years, you're a little bit shy of that second doubling, which means you're between 3 and 4 times. That gives you a good way to kind of handle that and to approximate it. A lot of times a good quick way to ballpark things allows you to sanity check your work. It also allows you to do some good stuff with it. So we now have f over p. We might want to, at this point, if we want to find the future worth, we could just multiply this by an actual present value. We would get f. We could also find out, if I knew the future value, how do I get the present? I just flip it, which means this has to be equal to 1 plus r to the minus k, which is just do 1 over that. But that is also usually tabulated so people don't do division mistakes. So this is one of those nice things. Now, what would happen if I let this run out to infinity? Right? Allow my compounding periods we talked about to go to continuous compounding. It actually approaches E. So I have some commentary on that in my Keith on Engineering Design. I'm not going to spend a lot of time on it because that's not a major emphasis here. But it is kind of a fun thing to be familiar with, one of the areas where you can find E dropping out for us. Now, so these are 2 of the factors. We're going to deal with 3 factors: present worth, future worth, and annuities. There's other ones too. There's, gradient payments and things like that. But these 3 letters dominate what's going on in basic finance. An annuity is originally it's an annual payment, but we can take a look at a monthly payment or things like that. As far as we're concerned as engineers, A is a constant valued payment. So let's say that I want to pull out of something, $1,000 a month or whatever. Or if I'm going to make payments at $1,000 a month, this is how you calculate when you're doing car payments. You have borrowed a present worth of things and you're going to make payments every month at X amount of dollars per month. So you've got to make sure that your present value of what you're borrowing is equal to the annuity payment that's going on. Now the easiest way to figure out how to get an equation for that is, let's just consider this. Let's take a look at what the future worth is of it. I'm going to make a payment at the end of period 1. Alright, so I make a payment of amount A, and it's after the end of the first, let's say we're doing monthly periods and I'm paying for a certain number of years. We'll kind of keep the car idea down. So we've got 1 plus R to the NM, but it's after the first period. Right? Because you don't pay the second you drive the car off the lot. You pick up the present value at that point, you pay a month later. So it's 1 month later. And then, that's my first payment. I'll remove this. Right? Then I have to make a second payment a month later. And I keep this all the way down to when I eventually just pay the final payment and my debt is canceled. Now if you notice, there's a neat pattern to this whole thing. I can pull the A's out and I can write it as a summation. I have, right, so this is what I'm going to pay. That's projecting my annuities into the future. So this is the future worth of all the annuities I'm paying. I can take the present worth of what I'm borrowing and I can project it into the future by this equation. So I am finding here F over A. So if I take this and I divide by A, so I get the future worth of my annuities, that's equal to the sum of all of these. Well, that's the sum from some I, and now we got to see, what am I running from? Well, I'm running from 0, the last one, because I'm doing 1 plus R, so whatever this I is. Maybe I should do K instead of I, so we don't think of it as interest. Alright, so if I take 1 plus R to the 0, I get 1, which is the term that's multiplying here. And then this has to run all the way up to my largest term, which is NM minus 1. So I have this lovely summation here. Now, this is a fairly famous series that goes on, and it's got a simple expression to it. This is actually just worth, in our case, it's, if you're doing the series up to m minus 1, and from 0, k equals 0, of x to the k, that's equal to x to the m minus 1 over x minus 1. I have the proof of this stuck inside my notes, so I'm not going to go over it here. Again, it's just a cute piece of algebra as far as we're concerned. But for our case, our m minus 1 is nm minus 1. That's up here. So I've got our x, which is 1 plus r to the nm minus 1 all over 1 plus r minus 1. So that's taking the formula and translating it over. Now from this, I notice on the bottom I've got 1 plus r minus 1, so I just have r. So I have 1 plus r to the nm minus 1 over r. And that is equal to the future worth of an annuity payment that you are going to do. If I want to find out the annuity given a particular future worth, flip this, flip that, and you have your answer. So I now have a nice simple way that I can tabulate all these things up, and I can make formulas between them. If I want to find out present worth, I have a factor for figuring out future to present, I have future to annuity. I can use these two ones together and I can figure out an annuity to the present by combining these two formulas appropriately. I'm going to leave that as an exercise for you guys to do. Ask me if you're not able to do it, but I think if you don't try something, it won't really stick into them. It is also available in the online notes, but I really encourage you, don't look at the online notes of how we calculate this present worth factor, or it's sometimes called uniform series, stuff like that. Don't look at it until you've given it a serious try for it. Now we now know how to convert between these three factors. Once we have two formulas, three factors are taken care of, and that's why these are the only ones I ever really worry about. I can get the rest. Honestly, for most common interest rates, they're all tabulated out there too, or you can write a really simple program and you don't have to worry about this anymore. So now we know how to get those numbers that go into it. Now what we want to do is, what can we do with them? So let's just talk about a couple of the common metrics that are used to handle these costs that go on. One that we do a decent amount is EUAC, which is equivalent uniform annual cost. What we want to do for a EUAC is we're trying to take the present worth of, turned into an annuity factor, right, of what's going on. So I take, my annuity based on P, and that's going to be dependent on your interest rate and the period and all the rest of that. So I take this function. I'll just note that this is A over P based on R and K, right? The rate and the period that you go on. And I multiply the current present value of whatever it is, the money that I'm taking out, things like that. So that's how much money I'm having to pay out every single time period. But there's also, at the end of this, my product is worth something. So at the end of this, I've got a salvage value. And that's worth money, so it reduces my cost. And I'm going to take that final value and project it into an annuity as well. I consider the same exact interest rate. It's over the same period that we're doing it, and this is the salvage value, S. So if I take, what does it cost me to buy a piece of equipment, I can turn it into, for instance, an actual annual cost. How much did that cost me? And I find out how much at the end can I scrap this thing for or sell it off for. And I also project that back, and that's telling me how much am I paying every single year. So that's my equivalent uniform annual cost, or EUAC. Now there's a similar one to this, which is an equivalent uniform annual benefit, which is taking a look if I put an investment in. So I'll just note for your use, this is very similar to this idea. Let's say I have an investment that pays me an amount so much per year, but I have to use a certain amount of dollars to buy this thing. Right? So this is the money I'm getting back in, and from this I have to subtract. I paid a certain amount of money in, so I have to project a present worth into an annuity, which is based on the interest rate and K that it's at, and whatever money I had to sink into it originally. And so, how much money I get back minus the annual equivalent of what I put in gives me my equivalent uniform annual benefit from that investment. And we want to find out, do the things we're putting in here actually benefit? Two other ones that are fairly common is the net present worth that goes on. Net present worth is very similar to this, except I project it to the present. So we have a net present worth. Right? So if I've got something that I'm having to pay a certain amount on, or it cost me something that's on them, whatever you want to consider it, so I've got, an amount that each year is going on, and that's at interest R and K. I project that annuity back, and then I have to subtract its cost that I'm paying right at the start. So I get some benefit A every single year from this, and I project it back to the present, subtract what it cost me to do it. So this is kind of the present equivalent of this formula here. All right, so if I just multiply P over A times this cancels out, and I get P over A times A minus P. So just realize these are basically the same formulas. This is taking a look at as an annuity. This is taking a look at as a present value, but you often hear people talk about the net present worth of whatever is going on. The final one that's common for people to take a look at is the rate of return that's going on. And what we do is we want to find out for a rate of return, it uses the net present worth, and it says the rate of return is the value R such that the net present worth is equal to 0. It balances out your cost and your benefits. So if you choose to force NPW to 0, not making any money off it, that'll tell you what that rate of return was. So it's kind of a way of finding out what is the interest rate that would balance that. So that's what you're really kind of estimating, is on what interest are they paying me to lend that money, or what interest rate am I paying to get this particular product. Either way you want to take a look at it. Some other things you might want to consider that's going into them that affects your costs. People will talk about depreciation of an item that has to do with our salvage values again. There is something that is not counted in this. You actually can, as your item depreciates in value, you actually get a little bit better than this, because you can get tax credits, at least at the moment, based off of what the depreciation value is. And so usually you're able to depreciate at a standard rate. A common one is, people say 25% of its value per year. That's going on, and this is pretty typical for, like, for instance, a car thing. If you take off 25% of a value, let's say you bought a $20,000 car, after 1 year, take 25% off, it's now worth $15K. And that's pretty close to what your blue book will probably say to it, delta your model. But when I take 25% of 15K off, in other words, multiply by 0.75, I'll find that this is actually down to $11,250. And you can keep on going on this. Actually, out by the time you get to 10 years, it's down to like about $1,000 or something. And that, whatever's left over at the end, is your salvage value. But each year, I lost $5,000. So I can actually take that $5,000 and subtract it from my earnings, and then reduce the amount of taxes I had to pay, because it's a cost of doing business. So beyond just this, I actually get an extra benefit, which is the tax benefit on it. Now this can be a lot of work to calculate and track each one. So what usually accountants will do is a version of this called straight line depreciation, and they just take they calculate using this method the final value or salvage value of whatever's in, or you find salvage value some other way, and then you take your cost minus your salvage value and divide it by the number of periods you're going to take your depreciation on, and then you just take that every single year, and they just are therefore easily able to track it. That tends to kind of put most of your depreciation later. If you notice, you lose a lot of money up front, you don't lose a lot of it later, so it's not a fairly accurate one. So that tends to give you future benefit but not present benefit, and the future benefit is lost a little bit by dollars and inflation and things of this sort. So a lot of companies will use an accelerated method. The IRS recognizes one called accelerated cost recovery system, which takes that same C minus S, the cost of it minus the salvage value, and it just multiplies by a weight system. And they just give you a series of weights you can do, and they give you recovery periods, 3, 5, 7, or 10-year periods, and they just tell you how much you can actually deduct each year by just taking a fraction inside the IRS table. You just look up what year you're in, and what your recovery period is, either the 3, 5, 7, or 10, and you just multiply your cost minus salvage value times that, and that is the deduction. You might ask, why do I want to do this? Well, when you're trying to justify purchase of a product, designing something else, and you take a look at these, it's worth actually saying, plus there is, these areas, and it saves us this much, and you can actually count that deduction in here based on your company's tax savings, and include the tax savings in here to kind of boost up the benefit of it, to give a really a better idea of what's going on within it. So that gives you some ideas. Now, some other things that are worth noting about this, these same values for calculating, present worth, annuities, and that can also be used for handling non-renewable resources. So for instance, if I assume there is static consumption that's going on, say for instance I'm taking a look at gas. Now I have to make some assumptions here, assuming I have a constant supply, and gas is being produced very slowly. However, we don't know where all the gas is, so I don't have a perfect estimate of what it is. But for simplicity's sake, assume I knew everything that was there, right? I have a present pool of gas, I have annuities that are pulling out, that's going on, and I can take a look then at that consumption, how fast I'm going to be pulling these out. Now in some cases there are some buildups that's going in and things of this sort, and so I might be able to do them like trees or things like that. If I'm doing wood, there is a return on them, so I can actually take a look at growth on those, and I can use my P over A factors to calculate those. So the same thing I do for money, I can actually do for any resource that is either renewable or non-renewable, just assuming the same type of factors that go on to them. So I talk a little bit about that inside the book that's on there. It's or my Keith on Engineering Design. It's worth knowing these same factors are useful to us there, but I'm not going to spend too much time on this one because I'm mainly trying to talk about money here. But it's worth realizing there's a tie-in. Don't just eject this as soon as you're done. Costs, Now the only remaining thing that I need to mention to you is a little bit how do we estimate costs that are out there. So there's one that we have that we call the engineering cost estimate method. Let me clear this off. The engineering cost estimate method. And what we're going to do in this one is it's kind of a bottom-up type design. It's so you can kind of consider this a object-oriented type thing that goes on. So what we do is we estimate the cost of each sub area in the thing, object-wise, and it's detailed, it's very accurate, and we build up the cost of what does it actually take to build this. All right, so this is kind of a bottom-up design. And we essentially take a look at everything necessary to produce an item. All right, so I have my raw materials that come in, and my raw materials have to go through a series of processes, and eventually I produce a final product. To know how much this final product is worth, I have to take a look at how much does each of these processes cost, and what does the initial raw materials that were coming into it cost. And so I just find out this one is equal to, and I sum them all up. In order to do this, I have to have a good work breakdown structure. I've got to really know what's going on at every stage. How much material does it cost? How much waste does it cost? So it's extremely accurate, because I add up all my labor, all my materials, all my overhead, all my whatevers. Right? But it's commensurately very accurate, right? Which means I'm going to be spending a lot of time trying to do this. So I would rather not have to do an engineering cost estimate method as it goes off. Another way that's often done is called a round table method. A round table cost estimate method. A round table one, what that means, a round table, it's kind of like, the Knights of the Round Table kicking back. You get a bunch of experts, hence the round table, who sit around This usually has, engineering people in the different disciplines, manufacturing, so on and so forth. Everybody from them, human resources, whatever, and each one takes a look at the kind of overarching plan and makes estimates. Now, if you have experienced people, they've gone through this and they got a pretty good idea where these costs are going, so they can give you a pretty good estimate of this process without having to actually go into that process, and it's usually pretty accurate. So this is a good approximation of that by just relying on experts in your system. What if you don't have experts? Okay, now what we have to do is we can do what's called an actual cost extrapolation method, and the actual cost extrapolation method says take the prototype you built, and then from that, it's very accurate. You know what your costs really were, but it's not always exactly what's going to happen, and you can extrapolate what that's going to mean to your final process. Again, it's not a guaranteed thing, but at least you know what really was involved in this particular system, and therefore you can try to draw those out. So you can use your prototype to estimate the final cost. The reason why it's an estimate, people might be saying, no, it should be exactly that. Well, when you go into mass production, there's tooling buildups, there's certain points where you have paid off that tooling, and then it's now very cheap to produce them, so it depends on the rate of production and the cost for tooling set up for large scale runs. So your prototype is not a perfect estimate for it, but it's a pretty good one. Another one that comes in, so this is the actual cost estimation. There's another one which is the analogy cost estimation method. The analogy cost estimation method means we're going to draw an analogy with an existing product. So we say this product is like that product, and then we can find out where the differences are and try to put some cost modifiers. This is a very simple method. It really relies on, do you have good historical data, how your company works, comparison to competitors and things of that sort. But it will usually give you a good rough order of magnitude of what you're doing. So, analogies, maybe I should call this one a prototype, although it's technically called actual cost. The other thing you can do as a method is a parametric or statistical estimation. Parametric estimation method, sometimes also called statistical, right? So the parametric or statistical estimation method, basically you have a large database. It kind of takes this analogy one, to the nth degree. I want analogies with a large number of ones, so I build up this database of similar systems, and I use that to estimate the costs from it. And it's kind of a multiple analogy cost method. Therefore, it potentially gives me a good connection. There are ways this can give problems, if there's no relations, if, there's a relation to the cost, but it's not causal, you could be missing variables. So there's a lot of things that can go on and cause problems in this. I cover this in a lot of detail in the actual online notes, so I don't want to waste too much time on this, but I do want to give big overview ideas of where can the problems happen. What happens if they're codependent, things to this. So there's a lot of potential dependence that goes on here, but we can exploit some of that to get a cost estimate that happens on. So that at least gives us a couple ways that we can kind of ballpark what's actually going on with each one of these. So, this is, I guess you could say kind of the gold standard, and these are ways that I can kind of estimate that without having to go through this horrible, tedious process that's going on. So, that's our kind of areas that it breaks down, right? Remember, it's round table, group of experts taking an educated guess. The actual cost, i.e. use the prototype to extrapolate to here. Analogy, where you take a look at some similar products or a similar product and extrapolate to here. and then the parametric statistical, where we take a whole lot of analogies with some parametric information and then try to extrapolate to here. That gives you an idea how you can get the costs, and then how you can relate that to, various terms that people in the finance department are going to want to use to cost this, that you can use to justify your products and explain what the cost and the benefits to your companies are. So we'll talk more about this in class, do some examples, and I will see you then. Bye.